Everyone, and welcome to this explainer. Today, we are diving into a massive piece of AI news that is quite literally revolutionizing how we simulate the physical world. If you've been following the artificial intelligence space for a while, you already know that bridging the gap between digital AI and real-world physical simulations has just been this massive hurdle. Well, today, we're looking at a brand new paper titled LLT, Local Linear Transformer for PDE Operator Learning. This is a profound leap forward in scientific machine learning, and it fundamentally changes the math on exactly how fast we can train AI to understand physics. So let's just dive right into it. Here is a quick look at our roadmap for today. We'll start with the PDE bottleneck, touch on the challenges of operator training, and then get right into the LLT breakthrough itself. After that, we'll cover its attention mechanics, the benchmark numbers, and what this all means for the future.
All right, part 1, the PDE simulation bottleneck.
To really ground ourselves here, we have to ask a pretty basic question. Why is simulating the physical world just so incredibly slow? Look, if you want to simulate car aerodynamics, fluid dynamics in a pipe, or the stress on an airplane wing, you rely on PDEs, partial differential equations. These are the mathematical equations that govern the laws of physics. But computing them using traditional numerical methods takes an immense amount of time. You have to break the physical space down into a grid or a mesh and basically calculate the physics step by step, node by node. For complex 3D environments, this can literally take supercomputers days or even weeks to process just a single simulation.
Enter neural operators. These scientific machine learning models offer a massive shortcut. Instead of calculating the math step by step for every single new scenario, a neural operator learns the underlying solution operator itself. Once it's trained, it maps the input, say the geometric shape of a car, directly to the output, like the aerodynamic drag. This completely bypasses traditional numerical methods, giving us near instantaneous results for new parameters. It's a total paradigm shift from calculation straight to prediction.
Moving on to part 2, challenges and operator learning.
But as you know, there is no free lunch in AI. Training these neural operators brings on a whole new set of massive headaches. As recent foundational research into variational frameworks, like the VRBA model, really highlights, optimizing these neural networks is notoriously difficult. The parameter optimization is high-dimensional and non-convex. Basically, that means the AI can easily get lost in mathematical blind alleys, effectively learning the wrong physics. Plus, when you introduce sharp transitions, like a shockwave in fluid dynamics, the residual errors spike. You get these high-variance loss estimators, creating a really messy signal-to-noise ratio that just slows training down to a crawl.
So how have researchers been trying to fix this up until now? Well, current frameworks generally try to patch these hurdles using some incredibly complex adaptive strategies. They try to identify the regions with high errors, apply adaptive sampling to force computational power into those specific areas, and then use residual-based importance weighting just to smooth out the variance. It's this massive, complex balancing act just to keep the training on track. But what if, instead of trying to patch the optimization process, we just fix the underlying architecture of the neural network itself?
Which brings us to part 3, the LLT architecture breakthrough.
That exact idea leads us to why we needed a pivot. We know the training is a huge bottleneck. And while standard transformers, the kind powering things like ChatGPT, seem like the holy grail for AI right now, they actually have a fatal flaw when it comes to physics. Standard transformers use global attention that scales quadratically, meaning if you double the number of computational nodes in your physical mesh, the compute time quadruples. It's brutal. Plus, they don't inherently understand local physical geometry. The newly introduced local linear transformer, or LLT, solves this beautifully. It scales linearly. So if you double the nodes, the compute time only doubles, all while explicitly incorporating coordinate and geometry information through local spatial mixing.
Let's dig into how that works in part 4, global attention, local mixing.
So how does the LLT architecture actually pull off this linear scaling under the hood? It does it by combining linear global attention with local spatial mixing. It's given us the best of both worlds. In physics, you absolutely need to understand both the macro forces affecting the entire environment and the micro interactions happening right next door between adjacent molecules or mesh nodes. Traditional models force you to pick one or the other or pay a massive computational penalty to try and do both. LLT does both, and it does it efficiently.
Think of it kind of like a giant city traffic system. Global attention is providing the macro bird's-eye view of the entire grid, watching citywide congestion and long-range dependencies. Meanwhile, local spatial mixing is the driver. It's paying strict attention to the cars immediately in your lane and the geometry of the road right in front of you. By separating these two tasks, but allowing them to inform each other within the transformer, LLT sidesteps that quadratic scaling trap completely.
Okay, part 5, benchmark results and speedups. Theory is great, but let's look at the actual payoff. We need to see the concrete numbers that prove why this is such a massive breakthrough for AI. Here is the headline number, 1.8 to 2.5 times. The LLT architecture cuts wall clock training time per iteration by an incredible 1.8 to 2.5 times compared to previous state-of-the-art models like Transolver, specifically on matched structured discretizations. We are talking about practically doubling the speed at which we can train these complex physical AI models, and doing it without losing any accuracy.
And what's super impressive is LLT's versatility. It's not just fast on one narrow type of math. The researchers benchmarked this across a huge variety of physical tasks: elasticity, plasticity, airflow flow, pipe flow, Darcy flow. It maintained competitive or even lower relative L2 errors across completely different mathematical discretizations. We're talking finite element, finite volume, finite difference, and it worked flawlessly on both perfectly structured grids and really messy, unstructured meshes.
To truly push the limits here, they stress-tested the approach on complex, three-dimensional car aerodynamics datasets. This is normally where older models would just crash or stall out because they hit memory limits. But LLT flawlessly handled over 32,186 unstructured mesh points per single sample. It maintained highly accurate and computationally efficient operator learning at a scale that is genuinely useful for real-world engineering and design.
Finally, part 6, the future of SciML. By shattering this PDE bottleneck through a much more intelligent architecture, LLT is unlocking something massive for the field. We are shifting away from an era where simulating reality took weeks of supercomputer time right into an era where neural operators can pull it off in milliseconds. The local linear transformer proves that we can train these models faster, at larger scales, and on much more complex geometries than we ever could before. With real-time physical AI rapidly becoming a reality, it really leaves us with one provocative question to end on. What would you simulate, design, or invent today if compute time was no longer an issue? Thank you so much for joining me for this explainer.